This video will continue our discussion of Chapter 10, where we're focused on studying two parameters as compared to each other. So we'll learn about paired samples in this video. We'll perform hypothesis tests for paired samples and interpret those results, and also look at two population proportions and hypothesis tests. In the previous video for Chapter 10, we focused on independent samples. Well, now we're going to focus on paired samples, which are dependent. Samples are selected in such a way that the values from one sample are matched to the values for another sample. And what we're trying to do is see if there's a factor here that causes a difference between the two samples. This can be a before and after treatment kind of effect, or just some kind of matched samples, such as testing a new paint mix versus an old one, testing differences in gas mileage comparing regular and premium gas, people's weight before and after a diet program. To be able to perform this analysis, we really want to focus on the difference for a subject before and after the treatment. So what we want to know is there a difference after compared to before? So we usually take the after value and subtract the before value. This is called the first difference, or the paired difference. This I really just indicates for an individual subject or automobile that we're looking at. The point estimate then for how much difference this factor is actually causing is d bar. So we sum up all of the differences that we calculate for each individual and divide by how many differences we added in there. That gives us the average paired difference. The sample standard deviation is calculated in much the way we've seen before. How far is an individual difference from the average? We square that, add those all up, divide by n minus 1, and take the square root of that. N is actually the number of paired samples, or the number of individual items that we're looking at. We can calculate a confidence interval for paired samples. So we would use that point estimate, the average of all of those paired differences, plus or minus the t-critical value times the standard error. That standard deviation we just looked at a moment ago, divided by the square root of n. In this case, we have n minus 1 degrees of freedom. And the test statistic for doing hypothesis testing to see if the factor truly is making the believed difference is a t-score, where we take the point estimate minus the hypothesized mean divided by that standard error. We would find a t-critical value using n minus 1 degrees of freedom. And we treat the hypotheses how we've treated them in the past. If we believe that factor is decreasing the value, then our alternative hypothesis would be that the average difference is something less than 0. So we could talk about sending workers to training, and we want to show that that training is decreasing complaints from our customers. So then we would try to test to prove that the average difference is something less than 0 in terms of complaints. That would be a lower tail test. After treatment would have to have so many fewer complaints than before treatment that that sample difference would have to be way, way, way below our hypothesized value. We get a t-critical value to determine the rejection region, and we're going to reject the null if our t-score is down in the rejection region. We can do an upper tail test where we believe that we've added productivity, for example, in a worker. We've given a worker some training, and they're able to produce more after the training than they were before the training. So that treatment effect would mean we believe that the mean difference is actually something positive, and we want to prove that that training really matters. Our alternative hypothesis would be that the mean difference is greater than 0, and we'd need to see productivity after training that was significantly higher than before training, and we'd get a t-score that was significantly above our 0. We could also do a two-tail test. We're not sure if there's a difference in the gas mileage between premium and regular gasoline. We just want to see if there is a difference. So we test to see if the gas mileage is the same with premium and regular or something different. We don't care if we get values way far away to the low end or way far away to the high end. We just want to see if these two gasolines perform differently. So let's look at a paired example. Suppose that you're a human resource executive and you send your salespeople to a customer service training workshop. You want to determine, is this training effective? You'd want to do this if you want to know if you're spending the company's money wisely. Why send people to training if that training is not actually helping the company? So each row in our spreadsheet will represent an individual or an item of interest. In this case, this is a salesperson, CB. Another salesperson, TF, and so on. The data in the columns represent this person. So CB had 6 complaints before training and 4 complaints after training. CB's difference is 4 minus 6, or -2. We'd always do the after minus the before so that we can see the change. TF had 20 and then 6, so -14, and so on. To do the mean difference, we add up all of those differences, that's 21, divide by 5 to get negative 4.2. So on average, complaints went down by 4.2. Now you might look at that and go, yeah, this training is really working. But we need to know if that's statistically different from 0, statistically below 0. We can also calculate the sample standard deviation, which I've done already, that's 5.67. Now we want to know if training has made a difference. So let's test this at the 5% level. Let's see if the behavior is the same before training as it is after training, or if the behavior has changed. Do we get fewer or more complaints after training? If we're going to test at the 5% level, then alpha is 5%. That's the area in the two tails. We've got 5 minus 1, or 4, degrees of freedom. We can use t.inv.2t in Excel to find this critical value of 2.7765. We can calculate our test statistic, or our t-score, to see how far away from 0 our sample mean difference actually is. So our sample mean difference was negative 4.2. We plug in negative 4.2 there. Our hypothesized mean difference is 0. So we plug 0 in there. That standard deviation was 5.6 divided by the square root of 5. Our test statistic, or t-score, is minus 1.66. So our negative 4.2 is only 1.66 standard deviations below 0. In order to reject the null, we needed to be 2.7765 standard deviations or more away from 0, and we didn't get that in this particular sample. Our test statistic is not in the rejection region, so at this point we do not have enough evidence to conclude that this human resources training is actually beneficial. If you were interested in getting more information before you just canceled this workshop for your employees, you might take a larger sample. You could get better information from a larger sample than you could from only 5. We also want to be able to do estimation and hypothesis testing for two population proportions. We're going to need the assumption of normality. To do that, we need the sample size times the population proportion to be greater than or equal to 5, and the sample size times 1 minus that population proportion also greater than or equal to 5 for both of the populations that we're looking at. The point estimate for the difference between the population proportions is the sample proportion for one minus the sample proportion for the other. We can also calculate a confidence interval if we wanted to know the confidence interval for the difference between the population proportions. We'd start off with our point estimate, P1 minus P2, plus or minus a z critical value. We've got a normally distributed sampling distribution, so we can use this z critical value times the square root of P1 times 1 minus P1 over N1. That looks like our standard error from when we were working with a single population proportion before. And we just add the standard error for the other proportion and then take the square root of all of that. So our hypothesis tests will look very similar to what we've done for the other cases of two population parameters compared to each other. If we are trying to prove that the population proportion for the first population is less than the population proportion for the second population, that will be our alternative hypothesis, and it will be a lower tail test. When we're actually doing the calculation, we'll be testing that the population proportion of 1 minus the population proportion of 2 is statistically lower than 0. Similar kind of thing for an upper tail test. Assume that we believe the population proportion for the first population is greater than the second, then we're really testing to see if that difference between the population proportions is greater than 0, and that will give us an upper tail test. We can also do a two-tail test. We might believe there's a difference between two population proportions. We might believe that women support a political proposition in a different proportion than men support that same proposition. So we might want to be testing to prove that their behavior or beliefs on a proposition are different. To do that test, we'll calculate the difference, and we just want to see that that difference is something different from 0. Since we begin by assuming the null hypothesis is true, we assume that the true population proportion for the first population is equal to the second population's proportion. And we can pool the two P estimates as follows. P bar equals N1 times P1, our sample size from the first population, times our sample proportion, plus N2 times P2, that's our sample size and sample proportion from the second population, divided by N plus 1. This works out to be x1 plus x2, the number of people in the first sample that have the characteristic of interest, and the number of people from the second sample that have that characteristic of interest, divided by the two sample sizes added together. To calculate our test statistic for our hypothesis test, we do the point estimate, so the sample proportion minus the sample proportion for those two samples, minus the hypothesized difference between the two population proportions. Divide by the standard error. Because of the assumptions made above, we will use this pooled estimate to calculate our standard error, and the tests are done in the same fashion as the other tests. If we believe that the population proportion for 1 is less than the population proportion for 2, then we believe pi 1 minus pi 2 is less than 0. We want to get a test statistic that's significantly below 0, so far below 0 that it falls in our rejection region, and that would allow us to reject the null hypothesis. An upper tail test would mean we believe the first population's proportion is significantly greater than the second, so the difference between the two would be greater than 0. We need a z-score then that it's significantly greater than 0, and that would allow us to reject the null hypothesis. We can also do that two-tailed test, where we'll split our level of significance between the two tails, and as long as we get a z-score that falls in one of those two tails, we can reject the null hypothesis. So an example for us to consider. Suppose we want to know if there is a significant difference between the proportion of men and the proportion of women who will vote yes on proposition A. In a random sample, 36 of 72 men and 31 of 50 women indicated that they would vote yes for that proposition. Let's test our hypothesis at the 5% level of significance. So we want to know if men and women would vote differently from each other. That's a two-tailed test. Is the population proportion different for men than it is for women? We'll start by assuming that men and women are not different from each other in terms of their preferences, and we'll try to prove that they are different from each other. The sample proportions for these two groups are the number that have the characteristic of interest divided by the sample size. So for men, that was 36 out of 72, or 0.5. For women, that was 31 out of 50, or 0.62. The pooled estimate for the overall proportion that we need to be able to calculate that standard error is x1 plus x2 over n1 plus n2. So 36 plus 31 over 72 plus 50, we get 67 out of 122, or 0.549. If we're doing a 5% test, and this is a two-tailed test, our z-critical value is 1.96. So the difference between the sample proportions needs to be at least 1.96 standard deviations below 0 or above 0 for us to reject the null hypothesis and conclude that men and women vote differently. So we'll calculate our z-score here. The sample proportion for men was 0.5 minus the sample proportion for women, which was 0.62. Our hypothesized mean difference was 0, and then we divide by the square root of that pooled estimate times 1 minus the pooled estimate times 1 over each of those sample sizes added together. Take the square root of that to get that into a standard error. Our z-score here is negative 1.31. So the difference in the sample proportions is 1.31 standard deviations below 0. But that's not far enough away from 0 for us to reject the null hypothesis. We needed to see a difference in sample proportions that was more than 1.96 standard deviations away from 0 in order to reject the null. At this point, we do not have significant evidence that men and women vote differently.